Good morning. Today we will see some more problems. Uh, Today we are going to study the most important problems from the chapter, that if we are given a certain total differential, and from that total differential, if we want to obtain the function f, so whether from the total differential it is possible for us to obtain the function f or not, it all depends on what is the nature of the given total differential. We have studied the condition for total differential, that if we have a total differential df in the form df equal to m dx plus n dy, where m and n both are the functions of x and y, then this total differential is said to be an exact differential if this total differential satisfies the condition that dou m by dou y is equal to dou n by dou x. So if this condition is satisfied by the given total differential, then the given total differential is said to be an exact differential. And if the given total differential is an exact differential, then only it is possible for us to obtain the function f from the given total differential. So if we if we compare the given total differential with this standard total differential df equal to m dx plus n dy, then we can write the expressions for m and n. So comparing these two expressions for df, we can write m is equal to y square minus y plus 2xy, and we get n is equal to x square minus x plus 2xy. So we obtain the expressions for m and n. Now differentiating m partially with respect to y and differentiating n partially with respect to x, let us obtain dou m by dou y and dou n by dou x and check whether these partial differentials are equal or not. So let us obtain dou m by dou y. Dou m by dou y will be 2y minus 1 plus 2x, and dou n by dou x will be equal to 2x minus 1 plus 2y. So if we observe these expressions for dou m by dou y and dou n by dou x, it is observed that the right hand sides of both these expressions are same. So what we can say is that, therefore we observe that dou m by dou y is equal to dou n by dou x. Here this m represents dou f by dou x and n represents dou f by dou y. So since we are differentiating m partially with respect to y and n partially with respect to x, this expression is nothing but the expressions dou 2f by dou x dou y and dou 2f by dou y dou x. So what we observe here is that the mixed second order partial derivatives of the given function f are equal, and if the mixed second order partial derivatives of the given function f are equal, we can say that the given total differential is an exact differential. And if the given total differential, since we observe that dou m by dou y is equal to dou n by dou x, we can continue. So since here we observe that dou m by dou y is equal to dou n by dou x, we can say that the given total differential satisfy the condition for an exact differential. Therefore we can say that df is an exact differential. So the first part of this given problem is over. So we have shown that the given total differential df is an exact differential. Now we want to proceed to the second part. Secondly, what we are asked to do is we are asked to determine the function f from the given total differential. So let us see how to obtain the function f from the given total differential. Here this first bracket is nothing but dou f by dou x, and it is equal to y square minus y plus 2xy, and this second bracket is nothing but dou f by dou y, and this is equal to x square minus x plus 2xy. So we have these expressions for dou f by dou x and dou f by dou y. Now in order to obtain the function f from this total differential, and since the given total differential is an exact differential, we can say that we can obtain the function f from the given total differential. Now in order to obtain the function f from this total differential, either we start from the expression for dou f by dou x, or we can start from the expression for dou f by dou y. Let us, for the sake of simplicity, let us start with the expression for dou f by dou x. We have dou f by dou x is equal to y square minus y plus 2xy. Now if we integrate this expression for dou f by dou x with respect to x, so this can be expressed as df is equal to y square minus y plus 2xy dx, and integrating both sides we get integration of df is f, and integration of y square minus y plus 2xy dx with respect to x is y square x minus y square minus yx plus 2x square y plus some terms containing only y plus some constant term. So this is the integration of the given function. This is the integration of given function. So this should be divided by 2. So this 2 will get cancelled. So integration of 2xy with respect to x will be 2x square y divided by 2. So that 2 and this 2 will cancel. So it gives y square x minus yx plus x square y plus fy, and this fy contains the terms containing only y, because when this f was partially differentiated with respect to x, the terms containing only y would have been cancelled out. So in order to take into consideration the terms in the given function f which contains only y, in which x was absent, we have to consider this term of fy, and in the given function f, if there was a certain numerical constant, that constant is taken into consideration with this constant of integration c. So this is the expression for f. Now our aim is to obtain the expression for the terms containing only y. We want to obtain this expression for fy, the terms in the given function containing only y. So for that purpose, what we can do is, since we have obtained this expression for f by integrating the expression for dou f by dou x, now differentiate this f partially with respect to y. Differentiating this f partially with respect to y, will get dou f by dou y. Dou f by dou y will be equal to 2yx minus x plus x square plus f dash y, and the differentiation of constant term with respect to y will be 0. So this is the expression for dou f by dou y by obtained by differentiating the expression for f we have obtained. Now this expression for dou f by dou y is compared with this expression for dou f by dou y in the given total differential. So if we compare these two expressions for dou f by dou y, what we observe is that here we have obtained dou f by dou y equal to 2xy minus x plus x square, and here dou f by dou y is x square minus x plus 2xy. So is there any additional term in this expression for dou f by dou y that contains only y? Not at all. So from this we obtain that the expression for f dash y is equal to 0. So comparing this expression for dou f by dou y and this expression for dou f by dou y, we get the term that f dash y is equal to 0, or this implies fy is equal to 0. So substituting this value of fy equal to 0 in this expression for f, what we shall get is, we get the expression for f, the function f from the given total differential that we have obtained. So substituting fy equal to 0 here, we get f is equal to y square x minus xy plus x square y plus c, because this fy is 0. So this is the function f that we can obtain from the given total differential. So this function f can be obtained from the given total differential if and only if the given total differential is an exact differential. If the given total differential is not exact differential, then it is not possible for us to obtain the function f from the given total differential. Now we can check whether, if we consider this f as the function of x and y, whether we get the same expression for df or not. So let us check the function that we have obtained is correct or not. That can be verified by differentiating f partially with respect to x and partially with respect to y, and using these expressions for dou f by dou x and dou f by dou y in the expression df is equal to dou f by dou x dx plus dou f by dou y dy. Let us check. So considering this f, differentiating it partially with respect to x, we get dou f by dou x will be equal to y square minus y plus 2xy, and differentiating f partially with respect to y, we get dou f by dou y is equal to twice xy minus x plus x square, and using these expressions for dou f by dou x and dou f by dou y here, we get therefore df is equal to dou f by dou x is y square minus y plus 2xy dx plus dou f by dou y is x square minus x plus 2xy dy. Do we get the same expression for df as given here? The two expressions for df are same. So whatever the function that we have obtained from this total differential is found to be the correct, right? Okay, so that is how we can obtain the function f from the given total differential. Okay, so let us see the next problem. Given that given that xu is equal to 1 plus au and yu is equal to bu cube, find rate of change of fxy equal to x e raised to minus y with respect to u. So you are given x as function of u, y as certain function of u, and f is the function of x and y expressed as x e raised to minus y. Then you are asked to obtain the expression for df by du. The rate of change of f with respect to u is nothing but df by du. You are asked to obtain the expression for df by du. So let us try to obtain the expression for df by du. Here we have to use the chain rule. If f is function of x and y, and each x and y are the functions of third variable u, then we can differentiate f with respect to u directly by using the concept of chain rule. So in accordance with the chain rule, df by du can be expressed as dou f by dou x into dx by du plus dou f by dou y into dy by du. So that is how we express df by du directly, where f is the function of x and y, and both x and y are the functions of u, and this is in accordance with the chain rule. Now from the given expressions for f and x u and y u, we can obtain the partial derivatives dou f by dou x, dou f by dou y, dx by du and dy by du, and using these expressions, in this expression we shall get the expression for rate of change of f directly with respect to u. So if f is equal to x e raised to minus y, what will be partial differential of f with respect to u, x? Dou f by dou x will be equal to e raised to minus y. Then differentiating f partially with respect to y, we get dou f by dou y will be equal to x e raised to minus y into differentiation of minus y with respect to y is minus 1. So this is equal to minus x e raised to minus y. So this is dou f by dou y. Since xu is equal to 1 plus au, what will be dx by du? Differentiating x with respect to u, we get dx by du is equal to a, and differentiating y with respect to u, that is dy by du. Since yu is equal to bu cube, we get dy by du is equal to 3bu square. So use these expressions for df by dx, df by dy, dx by du and dy by du. In this expression for df by du, we get df by du to be equal to dou f by dou x is e raised to minus y into dx by du is a plus dou f by dou y is minus x e raised to minus y into dy by du is 3b u square. So now in order to obtain dA by du, this is enough, but this is not complete solution or expression for dA by du. Here this expression for dA by du contains the terms of x and y. Here we are given the expressions for x and y in terms of u. So use these expressions for x and y here in order to get the complete solution for df by du. So replace x by 1 plus au and y by bu cube here. So we get this is equal to e raised to minus y. Y is du cube. So e raised to minus du cube into a plus into bracket minus of x. X is 1 plus au e raised to minus y is minus bu cube. So into 3bu square. Into 3bu square. So if we open up this bracket, or before we opening the bracket, we can take out e raised to minus bu cube common from these two terms. So this can be expressed as e raised to minus bu cube into bracket. And the first term, it will be only a minus this 3bu square, then minus 3bu square into au is 3abu cube. So this is the final expression for df by du. So this is the required expression for df by du. This expression is completely in terms of only u. So this is how we can obtain the expression for df by du, where f is the function of x and y, and both x and y are the functions of u. So that is about this problem. Then we'll see the next problem. Next problem is 13th one. If cos x raised to y is equal to sin y raised to x, you are asked to find dy by dx. If we are given that cos x raised to y is equal to sin y raised to x, you are asked to obtain the expression for dy by dx. So here we can use the concept of implicit function, because in the given expression it is not possible for us to separate x and y from one another. It is not possible for us to isolate x and y from one another. So even if it is not possible for us to isolate x and y, separate x and y, or to express y as completely the function of x or x as completely the function of y, still then it is possible for us to obtain dy by dx for the given expression. So for that purpose, what we need to do is we have to obtain the partial derivatives of f with respect to x and with respect to y. That is the expressions for dou f by dou x and dou f by dou y. And knowing the expressions for dou f by dou x and dou f by dou y, we can obtain the expression for dy by dx. We have seen that while studying the concept of implicit function, the expression for dy by dx is given by dy by dx is equal to minus of dou f by dou x divided by dou f by dou y. This is the expression for dy by dx for implicit function. So in the given expression, directly if we try to obtain dou f by dou x and dou f by dou y, it is not possible for us to obtain dou f by dou x and dou f by dou y directly. So for that purpose, what we need to do is we have to take the logarithm on both the sides. So taking log on both sides, we get y log cos x is equal to x log sin y. So by taking the logarithm on both sides of this expression, we get y log cos x is equal to x log sin y. And now differentiating this expression, here we can consider that f, the function of x and y, expressed as y log cos x minus x log sin y is equal to 0. So now we can differentiate this f partially with respect to x and with respect to y. So if we differentiate f partially with respect to x, we get dou f by dou x is equal to. So what will be dou f by dou x? Dou f by dou x will be y as it is. Differentiation of log of cos x is 1 upon cos x into differentiation of cos x with respect to x is minus sin x minus differentiation of x log sin y with respect to x is simply log of sin y. So this is this can be expressed as, so this is equal to minus y into sin x upon cos x is tan x minus log sin y, or this is nothing but minus into bracket y tan x plus log sin y. So this is the expression for dou f by dou x. Similarly, we can differentiate this f partially with respect to y. We get the expression for dou f by dou y to be equal to. Dou f by dou y will be differentiation of y log cos x with respect to y will be log of cos x minus differentiation of x log sin y with respect to y will be x into differentiation of log sin y with respect to y is 1 upon sin y into differentiation of sin y with respect to y is cos y. So this is nothing but equal to log cos x minus x into cos y upon sin y is cot y. So this is the expression for dou f by dou y. So we have obtained the expressions for dou f by dou x and dou f by dou y, and use these expressions for dou f by dou x and dou f by dou y here in the expression for dy by dx. So substituting the values of dou f by dou x and dou f by dou y in this expression, we get, therefore, dy by dx is equal to minus of dou f by dou x is minus into bracket y tan x plus log sin y divided by dou f by dou y is log cos x minus x cot y. So this minus minus will cancel. So we get the expression for dy by dx is equal to y tan x plus log sin y divided by log cos x minus x cot y. So this is how we can obtain dy by dx, though in the given expression it is not possible for us to separate x and y from one another, or in case of implicit functions, though it is not possible for us to express y in terms of x or x in terms of y completely, we cannot isolate x and y from one another, still then we can obtain the expression for dy by dx by using this expression. Dy by dx is equal to minus dou f by dou x upon dou f by dou y.